So what is a useful definition for energy in terms of how it can help us understand life? I mean, it's notoriously, we can define it mathematically and say kinetic energy is half mv squared and things like that. If you go to relativity, by the way, then you end up saying it's the component of the four vectors that points in the time direction. It's a thing that's conserved. That's why it's useful in physics. It's not created or destroyed. This is a deeply strange truth about the universe. From the Big Bang to today, all of the energy that ever was is still out there. This energy can change from one form to another, but all there is. So if energy is the thing that never goes away, what makes it so exquisitely helpful when we're trying to understand life, your life, my life, the moss on a stone, the bacteria under Antarctic ice? A good place to start is to say that energy is the capacity to make a difference. Not a hand-wavy difference, but a measurable directional difference to move something that wouldn't have moved to warm, something that would have cooled to assemble a structure that would otherwise have fallen to pieces. In physics, we encode those possibilities in tidy expressions: kinetic energy as 1/2 times mass times velocity squared, gravitational potential as mass times gravitational acceleration times height, and in relativity, time component of a four vector. But biology adds a beautifully practical refinement. It cares not just about how much energy there is, but about how available it is to do useful work. That availability has a name: free energy. Free energy is the currency of life. Picture the universe as a grand bookkeeping ledger with strict laws. Total energy is conserved, yes, but the usefulness of that energy is not. A cup of hot tea left on the table will cool to room temperature. The total energy in the room plus tea stays the same, but the portion you can harness to run a tiny turbine, if you fancied doing such a thing, declines. This spending down of usefulness is captured by the second law of thermodynamics and by a quantity called entropy, which loosely measures the number of ways the energy of a system can be arranged. High entropy means energy is smeared about in many indistinguishable microstates. Low entropy means energy is concentrated in a small set of arrangements, tidy, ready, harnessable. Life is a master accountant of free energy. Living things manage to keep pockets of low entropy, structured, highly specific molecules by continually exporting entropy to the surroundings. That's the essential trick. When your cells build a strand of DNA or a neuron resets after firing, the entropy within that local structure tends to drop, but the overall entropy of the cell plus its environment rises. There's no cheating the second law. Instead, life plays by the rules and wins anyway by coupling the reactions it wants, those that would otherwise be unfavorable to reactions that spill entropy into the wider world. The key word there, coupling, deserves lingering attention because it is the bridge between physics textbooks and the pulse in your wrist. Cellular machines don't merely use energy, they exploit differences in electrical potential across a membrane, differences in chemical concentrations, differences in temperature. Imagine a water wheel. The wheel doesn't turn simply because water exists. It turns because water falls. The fall is the difference. In cells, the waterfall might be a gradient of protons across a membrane. This is one of the most sublime commonalities in biology, bacteria, in hot vents, plants under the sun, and the mitochondria in your muscle cells all run on proton gradients, tiny electrical waterfalls of hydrogen ions. They let the ions flow down the gradient through molecular turbines called ATP synthases, and the result is adenosine triphosphate, ATP, the chemical coin that pays for just about everything else. Your whole life, in a sense, is powered by a ceaseless tide of protons finding their way downhill in exquisitely controlled ways. Why ATP? It's a molecule with 3 phosphates in a row, a spring under tension at the molecular scale. Clip off the last phosphate in a controlled reaction, and you free a small but reliable packet of Gibbs. Free energy, the biological accountant's preferred metric. We often write it as delta G equals delta H minus T, delta S spoken, the change in free energy, equals the change in enthalpy minus temperature times the change in entropy. Biology arranges for many small, safe delta G drops like careful steps down a staircase rather than one catastrophic plunge. That's how you extract useful work rather than setting yourself on fire, literally, since burning glucose in a flame and oxidizing it in your mitochondria lead to the same final energy tally, but with very different control over where the energy goes along the way. This brings us to the grand river that refills life's reservoirs of low entropy, the Sunday. Sunlight arrives at Earth in a torrent of visible and near-visible photons ordered high-quality energy, low in entropy, because it's concentrated in a relatively narrow range of wavelengths. Earth radiates back into space in the infrared, longer wavelengths, more diffuse, higher entropy radiation. The planet thus exports entropy to the cold of space while maintaining local pockets of order. life inserts itself into that cosmic exchange. Photosynthesis catches photons with pigment molecules, chlorophylls, and their cousins and nudges electrons into higher energy states. Those excited electrons are then stepped down through molecular circuits, pumping protons across membranes, forging our old friend ATP, and assembling carbon dioxide and water into sugars. Each step is arranged so that the overall energy book balances: no energy is created, none destroyed, but part of it is captured in the lower entropy form of chemical bonds that can be cashed out later. The rest is dumped as heat. So the miracle isn't that energy appears from sunlight, the miracle is the choreography that turns a floodlight into a blueprint. Not all life lives by light. Deep under oceans and inside rocks, chemoautotrophs tap other gradients, the chemical energy in hydrogen sulfide near vents, the redox differences between iron in one oxidation state and iron in another, or methane and oxygen where they meet. The principle is the same. Find a difference, couple your essential reactions to the dissipation of that difference, and you can bias the thermodynamic dice in favor of building and maintaining improbable structures like proteins, membranes, and you. You can feel the universality here. At every scale, from planetary climates to single enzymes, life is an engine of disequilibrium. Equilibrium is inert. It's the state where nothing interesting happens because all gradients are flattened. Life persists by staying near, but never at equilibrium, close enough that thermal noise can be exploited, but far enough that structure doesn't dissolve. The great Hungarian-born thinker Erwin Schrödinger called it feeding on negative entropy, and while the phrase is a bit poetic, the physics is sober: organisms import low entropy energy like sunlight, or reduced chemicals export higher entropy waste like heat and oxidized byproducts, and use the difference to keep their internal information-rich architecture intact. Now, if energy is the capacity to make a difference, we should also talk about information, because life is information heavy. A single bacterial cell carries megabytes of genetic instructions, all of it implemented in a noisy, jostling bath of water at body temperature. Keeping that information reliable costs free energy. Each time a molecular motor checks whether it's holding the correct amino acid or a DNA polymerase, proofreads a base, you're looking at tiny decisions that burn free energy to reduce uncertainty. There's a deep link here summarized in a principle from the physics of computation. Erasing a bit of information has an irreducible energetic cost paid as heat. This doesn't mean thoughts are expensive in the way a kettle is expensive. Rather, it means building, preserving, and correcting order, remembering rather than forgetting, must be coupled to some energy dissipation. The brain's quiet hum is in part the price of maintaining and updating reliable patterns in a thermally restless world. Let's return to that deceptively simple conservation law and ask a question that sounds philosophical but is really practical. What makes life feel so special if energy is always conserved anyway? The answer is that conservation tells you the size of the pot, but thermodynamics tells you how much of what's in the pot is spendable on building something interesting. A waterfall pooled flat is no longer a source of power, even though all the water is still there. The Sun-Earth system constantly recreates waterfalls of many kinds: light to heat, chemical to electrical, concentrated to dispersed, and living things position themselves where they can skim the cream of those cascades. The artistry is in the positioning. Consider metabolism as a network of energy trades. Glucose doesn't simply contain energy. Its carbon-hydrogen bonds represent a potential difference relative to oxygen in the air. Enzymes broker a stepwise détente between them, taking a small fee in ATP and reduce cofactors at each meeting. Those cofactors, nicotinamide adenine dinucleotide in its reduced form, and its cousins carry high-energy electrons to the membranes where proton gradients are maintained. It's market trading, but with nothing metaphorical about it. Prices are potentials, balance sheets are free, energies and defaults are death. Even growth itself, turning raw materials into a body, makes energetic sense when viewed as a contest between binding energy and thermal agitation. The shapes of proteins are favored because their folded forms settle into deep valleys on a rugged energy landscape. But to reach those valleys, newly made chains must explore many configurations. Thermal motion shakes them about, and molecular chaperones guide the journey, paying little fees of ATP to reduce the odds of getting trapped in a cul-de-sac. Once folded, proteins still wobble and breathe. They're dynamic, but they live in canyon floors where the return to order after a nudge is energetically favored. So order isn't a sculpture in marble, it is a dance sustained by constant spending. You might ask quite reasonably whether life fights entropy. It doesn't. It partners with it. A refrigerator doesn't violate the second law by making its interior cold. It simply dumps more heat out the back than it removes from the inside, and it does so by consuming electrical work. Your cells are like very clever, very tiny refrigerators with many rooms and many thermostats, each keeping certain parts colder in the entropy sense by shunting the cost to the surroundings. The bill arrives as heat. We can also connect this to cosmic history. The early universe was hot, smooth and simple, lots of energy, very little structure. As it expanded and cooled, differences emerged, slightly denser regions that would become galaxies, slightly cooler regions that allowed atoms to form, and later on young rocky planets under star-like chemical networks that could exploit persistent gradients. Life didn't appear despite the arrow of time. It appeared because there's an arrow of time, because the cosmos supplies a steady stream of low entropy energy sources and cold sinks that let structure keep cycling. The total energy content from the Big Bang to now hasn't budged, but its distribution, its usability has been endlessly remixed, and life is one of the most elaborate remixes we know. This perspective also suggests why the search for life elsewhere often focuses on environments rich in gradients. Liquid water is valuable not for mystical reasons, but because it is a superb medium for moving energy and matter around at just the right speeds. It supports membranes, dissolves a dazzling variety of chemicals, and buffers temperature. Add a steady energy source, a sun or chemical disequilibria in rocks and brines, and you've got the preconditions for coupling reactions into cycles that sustain themselves. We're not only hunting for habitable zones, but for exploitable differences: light versus dark, oxidized versus reduced, warm versus cool, concentrated versus dilute. Give chemistry a slope to run down and a cliff to climb, and you give it the chance to become biology. Let me tie this back to the opening. Claim energy is conserved. All there is all there is. That sounds static, but it's not. It's a promise that the drama lies in form rather than amount. The same total energy that rattled about in a primordial plasma now beats in your chest, pushes air through your lungs, crosses synapses as tiny ionic currents, and radiates from your skin into the surrounding night. It will diffuse and rediffuse long after we're gone. But while we're here, we live in the eddies, diverting a trickle of the cosmic flow into transient, exquisite order. The wonder is that this is allowed by the laws of physics, and not only allowed, but favoured given the right circumstances. If you want a single, useful, working definition of energy for understanding life, take this. Energy is the capacity to move a system from the ordinary to the specific, provided there's a gradient to cross and a mechanism to couple the crossing to work. Free energy counts the spendable portion of that capacity. Entropy tracks the price you pay into the universe's great account. And living things are the accountants. Curious, improvising accountants, forever balancing the books by spending high-quality energy to preserve information-rich forms, and forever meeting the second law with a polite bow and a flourish that says we know the rules and we know how to dance within them. So the next time you feel your heart quicken as you run up a hill, remember the river of protons turning the tiniest turbines, the hidden ledgers of free energy, opening and closing, the light of a star 8 minutes old arriving in your eyes, and the heat you shed to the air as your body keeps its patterns intact. All of it, every last jewel, is ancient. None of it is lost. It merely changes its tune as it passes through you. And that, I think, is a useful and beautiful way to begin to understand why energy is the thread that stitches living things to the wider cosmos. Why it was there at the beginning, and why it whispers still that all there is, all there, is enough to make life possible if you know how to spend it. Let's carry the thread a little further and make it practical. Practical in the way a cell is practical. Practical in the way a leaf is practical. We said energy is the capacity to move a system from the ordinary to the specific, provided there's a gradient and a way to couple motion to work. That phrase hides a universe. A gradient is simply a difference, and a coupler is a device or a process that lets one difference fund another. This is how a windmill turns airflow into rotation, and how ATP synthase turns a proton imbalance into a chemical bond. If you like metaphors, think of energy as height on a landscape. Nature is constantly rolling downhill. Biology is the art of installing ramps and gears so that, as matter slides downhill, here it is lifted up there, lifted into order, into function, into a shape that means something. Energy landscapes are not poetry, they are calculable surfaces. Every protein, every folded ribozyme, every membrane pore corresponds to a point on a vast landscape of possibilities. The stable shapes sit in valleys, wobbly shapes perch on hillsides. Thermal motion jostles the molecules about giving them chances to hop across small ridges. But here is the cleverness. Cells pay small amounts of free energy to lower the right ridges and raise the wrong ones. Molecular chaperones bind to new polypeptide chains and prevent disastrous misfolds. Proteasomes deliberately destroy damaged proteins, turning an unfortunate local arrangement into amino acids the cell can reuse. Destroying a misfolded protein looks like waste until you plot it on the energy ledger. The waste is a controlled dissipation that buys reliable function elsewhere. The second law is satisfied. The organism stays improbable in all the right ways. When we scale up from proteins to pathways, the same accounting holds. Consider central metabolism, the slow, dignified disassembly of glucose into carbon dioxide and water. In a flame, the reaction races to the end in a single rush of heat and light. In a cell, it walks 10 careful steps of glycolysis, the elegant pivot of pyruvate into acetyl groups, the steady drumbeat of the citric acid cycle, and the electron transport chain unspooling its power into a membrane. Each step yields packets of free energy in amounts small enough to be banked without combustion, mostly as ATP and as reduced cofactors. And those cofactors, carrying high-energy electrons, are spent not by touching oxygen directly, but by passing through a sequence of protein complexes that use the downhill slide to pump protons across a boundary. That boundary, the inner membrane of a mitochondrion, or the thylakoid membrane in a chloroplast, converts the chemical downhill into an electrical uphill. Now you have a gradient, and gradients are spendable. There is a quiet, beautiful physics in those membranes. A proton is not just a little bead with a charge. In water, it moves by hopping along chains of hydrogen-bonded molecules, a relay more than a march. The membrane, hydrophobic in its core, blocks the relay and forces protons to take special doorways, protein channels that open and close with atomic precision. The resulting separation of charge is a tiny battery, a voltage of tens to hundreds of millivolts across a span of a few nanometers. That's an electric field of millions of volts per meter harnessed without sparks or smoke. And sitting in that field, ATP synthase turns. It does not metaphorically turn. It rotates a molecular turbine, where protons flow through a ring of subunits, drives a central stalk that forces the catalytic sites to change shape, in sequence binding adenosine diphosphate and phosphate squeezing them into ATP, releasing the product. It is as literal as a water wheel and as precise as a watch. You can feel the engineering challenge. Too little proton motive force and ATP production stalls. Too much, and you generate reactive oxygen species, the misfired sparks of aerobic life which damage proteins, lipids, and DNA. Cells therefore uncouple when needed, opening controlled channels that let protons leak back without making ATP, converting chemical potential into heat. Brown adipose tissue in mammals uses this trick deliberately to warm the body. At first glance, it looks wasteful. But on the landscape, it's a safe path around a cliff, better to bleed off a little height as heat than to tumble in a cascade of oxidative damage. Temperature sits at the center of this balance. Hotter environments push molecules around more vigorously. Reactions speed up in a rule of thumb way captured by the Arrhenius equation. But beyond a point, thermal motion shakes delicate structures apart. Life, then, is a negotiation between kinetics and stability. Enzymes lower activation barriers so that necessary reactions proceed at comfortable temperatures. Membranes adjust their lipid compositions, more unsaturated tails for fluidity in the cold, more saturated for integrity in the heat. Proteins in thermophiles, the creatures that thrive in hot springs, are laced with extra internal bonds and hydrophobic cores that resist unfolding. Even this tuning follows the same principle. Spend a little free energy in making components that tilt the energy landscape in your favor. Save a lot by avoiding catastrophic loss of structure. Energy also shapes information processing in a very direct way. The brain, with its kilo upon kilo of tissue, spends a significant fraction of the body's resting energy budget, not on clever thought, but on maintaining ionic gradients across neuronal membranes and resetting them after each spike. Every time a neuron fires, sodium ions flood in and potassium ions flood out. Pumps must then push those ions back, step by ATP, funded step. Computation here is not a metaphysical process. It is a controlled movement of charged matter across barriers coupled to the hydrolysis of ATP. There's a reason neurobiologists talk of metabolic constraints on coding schemes. You can in principle represent information in many ways, but the brain's way is bounded by the cost of maintaining and updating the ionic differences that make bits reliable. The brain's elegance is to exploit noise thermal fluctuations. Instead of fighting it, arranging thresholds and synaptic weights, so that signals are robust without being energetically extravagant. We think with gradients. If we shift to ecosystems, the same calculus extends outward. Sunlight lands on leaves. A fraction becomes chemical order. Herbivores consume the leaves. Predators consume the herbivores. Decomposers return material to the pool. At each transfer, a large portion of the quality and the energy is lost as heat. The rule of thumb that only a small part, often about a tenth of the energy, moves up each trophic level is a statement about the costs of maintaining order at each step. This is why food webs taper, why apex predators are few, why the biosphere is green rather than tiger, striped. It is not a deficiency, it is the inevitable price of playing the game honestly with the second law. The planet remains vibrantly out of equilibrium because it bathes in low entropy sunlight and radiates high entropy infrared. Life is the intricate set of couplers that turn part of that flow into structure, song, and motion. Now, origins. How does the first coupler appear? There are many constructive ideas, but one of the most suggestive draws from the geochemistry of alkaline hydrothermal vents on the ocean floor. Their natural proton gradients exist between alkaline vent fluids and the mildly acidic ancient ocean, separated by thin walls of iron-sulfur minerals. Those walls can act like membranes, and the minerals can catalyze redox reactions. In such settings, chemistry can borrow the gradient for free, using it to push carbon dioxide and hydrogen along reaction pathways that build organic molecules. Primitive versions of the coupling machinery, metal clusters, and rudimentary peptides could have amplified the effect. Later membranes made of lipids would let protocells take their gradients with them, and proteins would evolve to replace mineral catalysts. It's an appealing story because it starts with differences that the planet supplies and retains the same physics that cells use today. The coupler comes first, or at least alongside, and metabolism becomes the scaffold on which information-bearing polymers evolve and improve. Notice how this picture demystifies and re-enchants at the same time. There is no violation of conservation, no energy is created. There is instead a continuous sorting of flows into channels, here for structure, there for heat, here for memory, there for motion. And because the details of coupling matter so much, evolution has room to explore. Natural selection is not a force in the Newtonian sense. It's a filter that keeps the designs that couple gradients efficiently while discarding those that can't pay their own bills. Over aeons, that simple preference yields extravagant novelty. Ribosomes. The factories that link amino acids into proteins emerge as rhythmic devices that translate stored information, which itself costs energy to maintain, into engines and scaffolds that harvest energy more effectively, and so on in a virtuous spiral. It is the closest thing we have to perpetual innovation, with the proviso that the clock is wound continuously by sunlight and geology. There are subtle, almost philosophical edges to this. Consider the famous thought experiment of Maxwell's demon, which imagines a tiny being sorting fast and slow gas molecules to lower entropy without doing work. For a long time, it seemed to hint at a loophole. But when you include the demon's memory, the information it must store and erase to do the sorting, the loophole closes. Erasing information has a minimum energetic cost paid as heat to the environment. The demon can win locally, only by paying globally. Cells are real-world demons that never get something-for-nothing proofreading. DNA lowers error rates at the price of hydrolyzing extra nucleotides. Sensory systems reduce uncertainty about the environment by expending ATP to run ion pumps and to manufacture receptor proteins. There is a bracing honesty here. Life does not magic order from nothing. It buys it fair and square. Planets buy it too. Earth's climate system is a grand heat-driven engine. Equator to pole temperature differences and day-night cycles create atmospheric and oceanic circulations. Weather is the way the planet moves energy from hot places to cold places, while producing eddies and turbulence that look random but are the signatures of dissipation. Against this background, living systems appear as fine structured appendices to the flow, intercepting a little here, spending a little there, and leaving traces in the geochemical record. Oxygen in the air, dark organic layers in sediments. Isotopic ratios that whisper of ancient metabolisms. Some researchers have proposed that life tends to organize in ways that increase total entropy production of the planet, plus life system, a principle called maximum entropy production. It's an intriguing idea, but it remains a hypothesis. What's solid is that life is compatible with, and indeed reliant upon, the increase of entropy overall. Where does this leave us in the very long run? The cosmic accounts settle slowly. Stars like our sun convert nuclear potential into light. Galaxies turn gravitational potential into the motion and heat of gas. Black holes grow as matter falls inward, radiating energy in the process. On these stages, life is a local pattern capitalizing on local cascades. The far future will be different, but the principle is the same. Patterns will exist as long as there are gradients and couplers to spend them. The scales may change, the details will differ, the ledger remains in balance. I think that's a restful thought. The laws are constant, and within them there is room for complexity wherever differences persist. So what should we carry into our everyday lives from all this? When you boil water for tea, you're watching energy quality degrade electric potential in a grid, becoming heat in a kettle, becoming microscopic motion in liquid water, becoming a gentle plume that warms your hands. When you walk up a hill, you convert chemical potential in sugars and fats into gravitational potential in your body's elevation, with much of the bookkeeping captured in ATP transactions and proton gradients. When you learn a new skill, your brain pays to lay down or strengthen synaptic connections. It burns a little extra glucose and oxygen to reduce uncertainty in its circuits and store reliable associations. None of this is metaphor. It is matter and energy moving in patterns your cells can afford, because the sun shines and the earth radiates. And if we turn back to the opening question, what definition of energy truly helps us understand life, we can refine it once more. Energy is the capacity to make and keep specific patterns in a world trending toward the ordinary by riding downhill differences and channeling their fall into uphill structure. Free energy counts the portion of that capacity that's still spendable. Entropy tallies the diffusion of possibilities as the price of doing business. Living systems are at their core reducers of uncertainty and builders of form, and their success is measured by how elegantly they couple to the differences around them. So when you look at a leaf, see a cascade of photons turned into a charged membrane, turned into sugars, turned into wood and fruit and fuel for the rest of the web. When you look at your hands, see muscle fibers using ATP to nudge myosin heads along actin tracks, tiny steps that reshape the world at human scale. When you breathe, hear the steady exchange of oxygen and carbon dioxide as part of a planetary conversation that began with ancient microbes and now includes you. All of it honors the conservation of energy, all of it respects the rise of entropy, and all of it flourishes in the space between the space where differences exist and clever couplers stand ready. The marvel then is not only that energy is conserved, but that the cosmos permits conservation to coexist with creativity. We live in the creativity for a while, and we pass the flow along. And if you listen closely in a quiet room, you might imagine you can hear the soft turning of a billion molecular turbines everywhere inside you, paying the tiny fees that keep your patterns bright against the dusk. Let's keep walking downstream from first principles and let the water widen into a river. We've said that life thrives by riding gradients with clever couplers turning downhill slides here into uphill structure there. That's the physics heartbeat behind metabolism, memory growth, and even evolution. But there's an even broader way to see it. Living systems are dissipative structures, order that not only survives in a flowing environment, but is made possible by the flow. This idea goes back to the thermodynamics of non-equilibrium. When energy moves steadily through matter, certain arrangements become stable because they channel the flow efficiently. Convection rolls in a heated fluid, the hexagonal cells of a Bernard pattern lightning like dendrites in a crystal, and on a more intricate level, cells, tissues, organisms, and ecosystems. The crucial insight is that order isn't a rebellion against the second law. It's one of the second law's favorite strategies for getting rid of gradients more quickly. So life is not a loophole. It's a professional gradient, smoother paid in sugar and sound and flight and thought. That framing does something profound to the story of evolution. Natural selection is often narrated as if it were purely about survival and reproduction abstracted from physics. But look closely and you see a thermodynamic through line. Structures and behaviors that couple more effectively to available gradients tend to persist. Leaves that position their chloroplasts to balance light capture against photodamage. Roots that explore chemical differences in soil. Predators whose muscles and nervous systems shape kinetic and informational flows with exquisite timing. Symbioses that stitch multiple metabolisms into a shared economy. These are all upgrades in energy coupling. Evolution then is a search algorithm wandering the landscape of possible couplers. It finds ribozymes that catalyze, it finds enzymes that accelerate millions-fold, it finds ion channels that open at just the right voltage. It finds molecular motors, myosin, kinesin, dynein, that stride along filaments, converting chemical-free energy into nanometer-scale steps. And it keeps the designs that pay their way. Let's pause on those motors. Kinesin is a two-footed walker, that drags cargoes along microtubule tracks inside cells. Each step is about 8 nanometers. Each step is fueled by one molecule of ATP. The motor coordinates its heads in a hand-over-hand gate biasing thermal motion so that random jostling becomes directed progress. It's a masterpiece of rectification. Take noisy fluctuations, open and close binding sites to break time symmetry, and you get net motion. The efficiency is astonishing. Under some loads, a respectable fraction of the chemical free energy can be turned into mechanical work. Not all of it, never all of it, but enough to explain how a neuron ships vesicles from the cell body to far-flung synapses, or how a developing embryo choreographs materials to the right places at the right times. We walk because countless tiny walkers inside us already learned the trick. Order built from noise is a recurring theme. Enzymes don't brute force reactions, they shape the energy landscape so that random motion is more likely to carry a molecule across the right barrier than the wrong one. Gene regulation doesn't eliminate fluctuations. It employs them with feedback loops that average out unwanted jitter and amplify signals that matter. Even at the level of development, how a fertilized egg becomes a body patterns emerge from reaction diffusion systems that turn smooth gradients into stripes and spots. The mathematics of these systems is the mathematics of flows and instabilities. Ride the energy through a medium with the right properties and patterns appear because they dissipate the driving differences more effectively than chaos would on its own. This perspective helps us think about sustainability too without leaving physics. A sustainable process is one that couples to renewable gradients differences that are maintained by planetary cycles rather than exhausting finite pockets of low entropy material. Photosynthesis couples to the daily gradient between incoming sunlight and outgoing infrared radiation. Winds and currents couple to temperature differences that persist as long as the sun shines on a spinning tilted Earth. Fossil fuels, in contrast, are the slow savings of ancient photosynthesis, chemical-free energy stockpiled over geological ages. Burn them quickly and you throw the ledger off balance, not in total energy terms that always balances, but in how and where the energy is distributed. Altering climate by trapping more infrared radiation, shifting gradients that weather and life have tuned themselves to over eons. Physics doesn't tell us what to value, but it does show the hidden hinges which flows we can ride indefinitely and which ones, if ridden too hard, reshape the stage itself. Let's come back to information because life is as much about remembering as it is about metabolizing. The thermodynamic cost of reliable information is reflected in the architecture of genetic storage and repair. DNA is chemically conservative, its backbone is sturdy, its bases pair with well-behaved rules. Its double-stranded form offers a built-in checksum. Each strand is a template to correct the other. Repair enzymes patrol the genome, excising damaged bases, restitching breaks, and proofreading newly synthesized stretches. All of that consumes free energy. But the investment pays out as fidelity, which in turn allows selection to work on meaningful variation rather than noise. Too much error and information dissolves, too little variation and adaptation stalls. Many organisms sit near an error threshold that balances cost against benefit, high enough mutation rates to explore, low enough to preserve. Even viruses, those minimalistic genetic economies, suppress and spend and adjust their error budgets because physics demands it. Brains refine the same trade-off. Biological computation measures and moves probability distributions. Synapses strengthen or weaken in proportion to statistical regularities in experience, a process that requires the persistent pumping of ions, the synthesis of proteins, and the reshaping of cytoskeletal scaffolds. Memory consolidation during sleep, those replayed patterns and slow oscillations, is an energetic project, a time when the brain reorganizes, pruning and reinforcing, paying now to save later on search and uncertainty. We sometimes romanticize thought as immaterial, but its dignity is not diminished by the bill at the end of the month. The bill is the reason it works at all. Paying for reliability is how a squishy, warm organ becomes the map of the world. It's tempting to ask whether there is an upper bound to how much order can be woven in a given place and time. There is no single number, because order depends on what you're measuring. But there are bounds on how much useful work can be extracted from a given flow set by exergy. The maximal portion of energy that can be converted into work as a system equilibrates with its environment. The concept is invaluable when you compare engines, ecosystems, and even cities. A city seen thermodynamically is a vast coupler. It intercepts flows of sunlight through food and climate, chemical potential in fuels and materials, and information in human minds and networks, and channels them into structure, roads, buildings, cultural artifacts, and into heat. always into heat. Two cities with the same total energy throughput can have very different exergy efficiencies depending on how well they coordinate their couplers, how much they recycle low-grade energy into useful niches, and how little they waste by letting high-quality differences flatten without doing anything interesting on the way. There's a related delicate concept called homeostasis that deserves a thermodynamic translation. We usually define it as keeping internal variables, temperature, pH, ion concentrations within life-friendly ranges. But physically, homeostasis is a control problem in a fluctuating environment. You can stabilize by building a vast buffer like a lake resisting daily heating and cooling, or by active feedback like sweating and shivering, or by predictive control like plants anticipating dawn and dusk with circadian clocks. All of these strategies cost free energy, and each has a characteristic signature in entropy production. A buffered system trades responsiveness for passive stability. An actively controlled system spends more to stay nimble. Evolution doesn't choose a single solution. It mixes and matches across tissues and timescales. The elegance is in the fit, the right control where it pays off most. We should talk too about aging, the slow, uneven fraying of patterns over time. Many hypotheses exist, but one useful prism is energetic. Mitochondria, while superb at extracting free energy from reduced carbon, are also the principal sources of reactive oxygen species. The cell has scavengers, superoxide dismutases, catalases, peroxidioxins, repair crews for lipids and proteins, and quality control systems like mitophagy to recycle damaged mitochondria. These protections cost energy. They're worth it. But across decades, tiny mismatches accumulate, especially in tissues that are high throughput and low renewal. DNA repair is excellent but not perfect. Proteins are replaced but not always with equal fidelity. Crosslinks form, garbage removal falters. In energetic terms, the couplers are worn but still running. The system can still pay its bills but with smaller margins. There's no single lever to pull because aging is not one process, but a choir of processes, each rooted in the physics of keeping in probable order in a world that never stops shaking. Cosmically, the same dance recurs at different scales. A star is a nuclear engine balancing pressure against gravity by turning mass into radiant energy. Its metabolism flows from core to surface to space, and its death is the exhaustion or redirection of that flow. A planet's weather is heat, seeking cold, complicated by rotation and topography. Its moods reflect the interplay of forcings and feedbacks. On such a planet, life adds an extra set of couplers that alter the baseline. Flows, vegetation, darkens land and moistens air. Microbes fix nitrogen and change the ocean's appetite for carbon. Forests pump water, making their own climate to some extent. These are not metaphors layered on physics. They are physics written in green and blue. And they remind us that energy and information are braided. A rainforest remembers its own existence, in the sense that its structure and functioning make the conditions for its persistence more likely tomorrow than today, until or unless the tide gradients shift. Which returns us to where we began. A useful definition of energy for life is the capacity to move a system from the ordinary to the specific by riding differences with couplers that bias motion into work. But perhaps we can refine it once more by bringing time to the foreground. Energy is also the tempo of change. With no flow, a structure can persist but not adapt. With too violent a flow, it can adapt but not persist. Life sits in the Goldilocks zone of flux, a regime where inputs and dissipation are steady enough to sustain patterns, yet variegated enough to coax novelty. Consider evolution's pacing bursts and plateaus, radiations after extinctions, slow accumulations under stable climates. These rhythms are not only ecological or genetic, they are hydrological, volcanic, solar. Time writes itself into biology because energy arrives in beats and pulses, and the best couplers learn not just what to do with the flow, but when. You might ask, does this grand thermodynamic unification leave room for meaning? I'd suggest it gives meaning a foundation rather than a ceiling. The taste of bread, the warmth of a hand, the thrill at a night sky, these are not reduced by understanding their flows. They are made possible by them, glucose turning into proton gradients, into neuronal firings, infrared photons leaving your skin into the winter air, faint starlight crossing space to be turned into signals in your retina and stories in your cortex. Knowing this connects the smallest motions to the broadest vistas. We are not apart from the account, we are its most articulate lines. And so picture a leaf in sunlight. Photons strike pigment, electrons are nudged, protons gather on one side of a membrane, ATP clicks into being, sugars take shape, sap flows, a caterpillar eats, a bird feeds, a child watches. Thoughts form, hands draw, words are spoken. At every step a gradient falls and a pattern rises, then falls again, passing the baton forward. All the while the total energy remains constant and the total entropy of the universe increases as it must. Yet in the middle distance, our distance, beauty and structure and memory bloom precisely because the universe allows and even encourages such local improbabilities as efficient routes to flatten differences. So if you carry one intuition into tomorrow, let it be this: the world is full of differences asking to be coupled. Life is the answer. Whether you're a cell coaxing ions across a membrane, a forest tugging on clouds, a lineage exploring new designs, or a mind arranging syllables into sense, you are participating in the same deep choreography. The music is the flow of energy. The steps are the couplers. The stage is time. And from the Big Bang's fire to the quiet room where you sit, all there is enough to make the dance continue, as long as we learn how to listen and how to spend it well. Let's widen the lens again and ask a deceptively simple question: how much flow does life actually ride? And how close does it come to the physical limits of what's possible? Energy is conserved, yes, but the quality of energy, the portion that can be harnessed as useful work, depends on contrasts. On Earth, the grandest contrast is between the hot, bright sun and the cold blackness of space. The planet absorbs a broad beam of sunlight and sheds a broader glow of infrared. In between, 1,000 nested engines, winds, currents, storms, forests, cities, cells catch eddies of that river. If you integrated all of it, the sun supplies on the order of 100 petawatts to the top of Earth's atmosphere. A smaller but still colossal share reaches the surface. Most becomes heat and is re-radiated. A fraction rearranges matter in interesting ways. That small fraction is enough. Enough to build mountains of cellulose spin hurricanes and keep 8 billion of us warm and thoughtful. There is a clean piece of physics that sets a ceiling on what any heat engine can do, from a steam turbine to a molecule-sized motor, the Carnot efficiency. It says that the best possible fraction of heat you can turn into work depends only on the temperature difference between your hot source and your cold sink. Bigger difference, more potential. For life on Earth's surface, the hot source is effectively the spectrum of sunlight absorbed by ground or leaf, and the cold sink is the sky into which infrared escapes. Photosynthesis does not operate as a simple heat engine. Its trick is to capture photons and use their quantum of energy to move electrons directly. But even then, the lesson carries: match your machinery to the contrasts you have. Plants filter the sun's spectrum through pigments tuned by evolution. They reflect green and absorb reds and blues, because that's where the biochemical ledgers balance most profitably. If you tried to make a leaf black to catch everything, you'd buy a little more light at the price of overheating and photo damage. In practice, the efficiencies we observe span a spectrum at the level of a single well-watered leaf under good light energy conversion into sugars can reach the high single digits of percent. Averaged across fields, seasons and clouds, it falls to low single digits. It sounds modest. It is astronomically productive when integrated over continents and years. The same honesty threads through animal metabolism. Aerobic respiration, burning sugars and fats with oxygen in the careful stepwise manner of mitochondria, can return a few dozen ATP molecules per glucose. Fermentation operating without oxygen returns only a small handful. That difference isn't a quirk. It's a map of how well each pathway couples to the available gradients. Oxygen is a powerful electron acceptor. It opens a deep downhill channel for those high-energy electrons to slide, raising the proton gradient higher and paying for more ATP clicks per molecule of food. When oxygen is scarce, cells accept a poorer exchange rate, less ATP, more byproducts, because a bad bank is better than none. Muscles sprint with fermentation, they stroll with respiration. The physics is kind, but it is never indulgent. If we zoom into the chemical choreography, cells achieve their feats by layering couplers. Proton gradients are the obvious engine rooms, but they're not alone. There are sodium gradients in bacteria, potassium biases in neurons, calcium pulses in signaling pathways, and phosphate springs in ATP, and its cousins, each a small reservoir of order that can be tapped against the noise of a warm, watery, the world. What looks like bewildering complexity is in fact a modular toolkit. Once evolution discovers a reliable way to store a tiny amount of free energy, it builds adapters, converters, and multiplexers. That modularity explains why life is both diverse and deeply conservative. The same ATP synthase family sits in bacteria and in your mitochondria. The same ion channels echo across species. It is the mark of a good coupler that it travels well. We should talk a little about the quantum underpinnings because they're often invoked with a mystical flourish when the truth is both subtler and more interesting. Quantum tunneling allows particles like protons and electrons to pass through energy barriers they couldn't classically climb. Coherence allows excitations to explore multiple paths simultaneously for brief instants. There's evidence that enzyme active sites are arranged so that tiny amounts of tunneling help certain reactions along, and that in some photosynthetic complexes, electronic excitations can sample paths through pigment networks in a way that appears wave-like on femtosecond timescales. Does biology use quantum weirdness? In a very grounded sense, yes, because at molecular scales everything is quantum. The open question is how far coherence survives in warm, wet conditions, and whether it confers an advantage beyond what classical hopping could achieve. Sensible researchers disagree on the degree, but they agree on the outcome that matters. Energy transfer and catalysis in life are astonishingly efficient. Efficient enough that any quantum benefits are complements to rather than replacements. For careful molecular design, we should avoid romanticizing. The achievements stand on their own. Here's a concrete, everyday illustration of the scale of these flows inside you. The chemical coin ATP is spent and reminted so rapidly that you turn over an amount on the order of your body weight every day. That doesn't mean you stockpile that much. It means the same molecules are cashed out and restamped again and again as electrons slide along their paths and protons come home through their turbines. It's a tiny high street with a very fast circulation. The numbers vary with activity and diet, but the image holds your life as a tight, bustling economy where cash changes hands constantly to keep specific patterns intact. Now consider information once more, but through the lens of limits. There's a beautiful bound derived from the physics of computation that says, erasing a single bit of information must dissipate at least a tiny packet of heat proportional to the absolute temperature times a constant times the natural logarithm of 2. In practice, our computers and our brains operate far above that ideal cost, but the bound is there whispering that remembering and forgetting will always have bills attached. This matters for biology because sensory systems and nervous systems are, among other things, uncertainty and reducers. They take a diffuse probability distribution over possible worlds and narrow it so the organism can act in time. Narrowing costs energy. This is one reason brains are greedy. They draw a generous share of the resting metabolic budget to run pumps, reset gradients, and rebuild synapses in line with experience. The reward is predictive power, the ability to anticipate the near future and to couple to it just a little better than chance. Let's lift our gaze from bodies to ecosystems and cities because the same bookkeeping applies. An ecosystem is a web of couplers that splits the incoming exergy, usable energy into many niches. Warmth that would have been lost as featureless heat is briefly tied up as structure and behavior. Then it is released, but not before it has supported a stunning variety of forms. A well-organized ecosystem tends to cascade energy. High-quality inputs are used first by organisms that can grasp them without waste. The leftovers, lower quality, more diffuse, are picked up by specialists adapted to squeeze value from scraps. Decomposers close the loop. Cities do something similar with fossil and solar flows, though far more sloppily. Two cities can draw similar total power, but differ dramatically in how often they pass the parcel before letting the last warmth out of the window. Good design of buildings, transport, food systems, and information networks is at root a quest to create graceful cascades rather than clumsy dumps. So the physics gives us not only constraints but targets. What about limits to growth in a physical sense? The planet's energy income is generous but not infinite. Its sinks, oceans, soils, forests are vast but not bottomless. You can accelerate a flow beyond the rate at which your couplers can safely dissipate the byproducts, and then the stage itself shifts. In climate terms, we've added greenhouse gases that trap more infrared radiation, tightening the gap between our hot source and cold sink and shifting circulation patterns. The physics here is uncontroversial. Change the radiative properties of the atmosphere, and you change the gradients that weather and life have learned to ride. Sustainable design in the strict physical sense means living within renewable contrasts, solar, wind, hydro, geothermal, while keeping the planetary sinks healthy enough to carry the entropy we export. That isn't a moral afterthought, it's the condition for long-lived complexity. Origins now return with a clearer face. The idea that life began by exploiting geochemical gradients, those provided across natural mineral membranes at alkaline vents, nicely prefigures the proton circuits seen in modern cells. Imagine a porous chimney of iron-sulfur compounds with alkaline fluid percolating up from beneath and more acidic ocean water bathing the outside. Across the thin mineral walls, a natural proton motive force exists. Add catalytic surfaces and simple organics and you have a setting where carbon dioxide and hydrogen can be coaxed into more energy-rich molecules. It's not that the first cells solved all of life's challenges at once. Rather, the planet offered a ready-made coupler, and chemistry that aligned with it could persist long enough to tinker with membranes, catalysts, and information polymers. The transition from borrowed gradients to own gradients, lipid membranes with embedded pumps, is a plausible pivot from geochemistry to true biochemistry. The continuity of the physics is the charm of this story. Astrobiology adopts the same logic when we look outward. We search for disequilibria pairs of gases that shouldn't coexist without a persistent source thermal patterns, suggestive of circulation, powered by a star surface colours that vary in ways consistent with pigments doing work. Oxygen and methane together can be a hint. So can a planet that glows in particular infrared bands, in a way that implies active weathering or outgassing. None of these on their own prove life. Worlds can be strange in many lifeless ways. But they all pose the right question: what couplers could exist here, given the available flows? And would any of them be the sorts of couplers that do chemistry that remembers? There's a deeper unification we can hazard without overreaching. Complexity appears where there are layered, semi-independent flows. A star by itself is a single magnificent engine with a relatively narrow set of behaviors. Add a rocky planet at the right distance with liquid water, and you gain new flows, hydrological, geological, chemical, each with its own timescale and bottlenecks. Add life, and you introduce enzymatic couplers that rewire the chemical networks, seeding feedbacks that can stabilize or destabilize climates. Add minds, and you bring in symbolic flows that can reorganize matter at a pace far faster than genes. At each layer, new forms of order arise because new differences exist to be exploited. There is no inevitability in the particulars, no guarantee of oak trees or octopuses, but there is a general permission wherever gradients overlap and timescales interleave patterns have room to become both resilient and inventive. Time then is not just a backdrop but a resource. Slow flows, continental drift, the carbon cycle provide reliable baselines. Fast flows, lightning strikes, gusts, neural spikes offer flashes of possibility. Life knits them together: enzymes that act in microseconds, proteins that fold in milliseconds, cells that divide in hours, organisms that grow in seasons, lineages that evolve in millennia. The art is in synchronization, circadian clocks anticipating dawn, trees timing flowering to the reliable slope of spring temperatures, neural cascades that unfold just quickly enough to catch a thrown ball. The best couplers are not only efficient, they're timely. We are creatures of tempo as much as of energy. If all of this seems very grand, bring it back to your desk or your kitchen. A kettle quietly demonstrates the difference between energy and exergy. Once the water boils further, heating doesn't make tea stronger. It lifts steam that carries away the extra order you paid for. A refrigerator cools its interior, warms your kitchen and pays an electricity bill. It's a small lesson that every local pocket of order is bought fair and square. A solar panel on a roof is a leaf of a different lineage, catching photons and pushing electrons down a circuit. Its effectiveness depends not only on sunlight, but on the coldness of the sky that ultimately accepts the waste heat. Cooking, walking, reading, these are not only metaphors, but exercises in coupling differences to purpose. So where next? If energy is the capacity to move a system from ordinary to specific by riding differences with well-tuned couplers, then the frontier is design biological, technological, and social designs that respect the limits and play to the strengths of our planetary flows. We will not escape the second law. We don't need to. We need to become better at catching high-quality inputs before they diffuse, passing them through as many useful hands as make sense, and letting them go without collateral damage when they've paid their way. That means membranes and markets, enzymes and institutions all tuned to the same rhythm: catch, convert, cascade, clear. And perhaps that's the most satisfying note to hold for a moment. The universe's deep rules, conservation of energy, increase of entropy, are not cold constraints. They're the staff lines on which all the melodies are written. Life is a long improvisation on a few themes: gradients, couplers, timing, and memory. So when you think of energy now, don't picture a number in a column. Picture a slope, a gate, and a wheel. Picture a photon nudging an electron. Picture a proton finding the right doorway home. Picture heat drifting away into the night, like the last chord fading. All there is enough if we learn patiently to spend it with style. Next, let's turn to two closely related questions that bring everything we've said to a sharp edge. How information is physically stored and transmitted in living matter from genes to brains to cultures, and how the laws we've explored set hard, beautiful limits on speed, accuracy, and memory. From the alphabet of DNA to the whispers between neurons, the patterns we keep are, at every step, paid for in tiny coins of free energy. Let's count them. Let's do what we promised. Count the coins of free energy that pay for information, how it's stored, moved, corrected, remembered, starting from the atom by atom ledger of DNA and climbing up to the whispers of neurons and the stories we share. The rule that frames it all is remarkably compact information is physical. It isn't a ghostly overlay. Bits live in states of matter, chemical bonds, ion gradients, conformations of proteins, voltages across membranes, and every reliable bit demands an energetic toll to set, to keep, or to erase. There's even a famous lower bound on that toll: erase a single bit, and you must release at least k times, t times, the natural log of 2, as heat an amount so small at room temperature that you can forget it while boiling a kettle, but so fundamental that it whispers, remembering and forgetting, have prices that no ingenuity can drive to zero. We can be clever about approaching the limit, but the limit is there. Start with genes. A strand of DNA is a long polymer with a sugar phosphate backbone. Information is written in the sequence of 4 bases. Truthfully, that sequence isn't magical. What makes it powerful is copyability. The double helix pairs bases in a complementary way, so each strand can serve as a template for the other. During replication, enzyme complexes unzip the helix and assemble a partner strand base by base. Mistakes happen, of course they do, because thermal jostling is constant and the chemistry isn't perfect. But cells pay extra to catch and correct errors. The replicative polymerases proofread, snipping out mismatches. Dedicated repair teams patrol for deaminations and oxidations. Mismatch repair compares the new strand to the original and patches where needed. The result is striking error rates after proofreading, and repair can fall to a few in a billion bases, copied sometimes better. That fidelity is not free. Each check consumes time and free energy. Each excision and resynthesis burns additional high-energy bonds. So life buys reliability by spending, and it spends because reliable information allows selection to act on genuine variation rather than noise. Even the structure of the genetic code, how triplets of bases map to amino acids, carries the imprint of error handling. Its redundant multiple triplets can specify the same amino acid, and near neighbors in the code often correspond to chemically similar amino acids, which cushions the effect of single base errors. It looks suspiciously like a code engineered for robustness under noise, and whether that arose by frozen accident or by selection for error tolerance, the thermodynamic reading is the same. The code is a mapping that reduces the damage per error, and thus reduces the energy a cell must later spend on quality control. A tidy economy of risk. Protein synthesis continues the arithmetic. To make a peptide bond, the cell spends several high-energy phosphates, one to load an amino acid onto its transfer RNA, others to advance and proofread on the ribosome, and one to seal the bond. That cost is well worth paying, because it buys function. The folded protein is a specific shape on an energy landscape that makes certain reactions easy, but folding itself is a search in a thermal bath. Random motion rattles the nascent chain. Chaperone proteins invest ATP to prevent bad knots and promote good folds. If a protein goes astray or is damaged, it's tagged for demolition and fed to a proteasome, where the chain is chopped back into amino acids. Again, apparent waste is revealed as prudent spending. When you tally the alternatives, it's cheaper in free energy terms to refold or recycle than to let malfunction propagate. From gene expression to gene regulation, we find an exquisite dance between noise and control. DNA isn't a static library, it has a soft architecture. Proteins bind to regulatory sites to recruit or block polymerases, histone tails are chemically adorned to loosen or tighten local packing, and loops bring distant segments together for crosstalk. These are physical interventions, each with an energetic footprint. They don't eliminate fluctuations, they shape them so that beneficial responsiveness is preserved while spurious chatter is damped. The decision to switch a gene on in response to a sugar appearing in the environment is at ground level, a tipping of free energy balances at specific binding sites. The accuracy of that decision, how often the cell is full, depends on how much energy it's willing to spend to check. Even microbes write and keep memories. Certain bacteria carry a remarkable tool now famous, an array of genetic repeats interspersed with fragments captured from the genomes of invading viruses. The array is transcribed into guides that direct a nuclease to cut matching viral sequences if they return. It's an immune memory written directly into DNA. It costs energy to capture, to maintain, to transcribe, to deploy, but the savings in survival and future repair are tremendous. We see here a deep pattern. Information improves coupling to the environment, but it isn't free. Organisms budget carefully. Let's climb to neurons, because brains make the price tag plain. A neuron at rest is not off. It holds differences: sodium ions high outside, potassium ions high inside, a negative resting potential, maintained by pumps that trade ATP for the right balance of ions. Each time a neuron fires, voltage-gated channels open and a wave of depolarization runs along the membrane. Afterwards, the gradients must be restored by the sodium-potassium pumps, each cycle of which spends 1 ATP to push 3 sodium ions out and 2 potassium ions in. Multiply that by countless channels and long axons, and the energy bill grows. It's no surprise that a brain, though only a small fraction of body mass, demands a disproportionately large share of resting energy. The bill pays for precision, reliable spikes with reproducible timing and synapses that can adjust their weights in meaningful ways. Speed, accuracy, trade-offs appear everywhere in neural hardware. An unmyelinated axon conducts impulses relatively slowly. Wrap it in myelin layers of insulating membrane, and the signal jumps between gaps, moving far faster with less leakage. That speed and energy efficiency aren't free. Myelin must be built and maintained by glial cells, and the axon's geometry must be tuned. Yet where timing matters, vision motor control, the investment repays itself handsomely. Similarly, synapses that release neurotransmitter reliably and reset quickly cost more than sloppy ones. Brains allocate those resources where the value of accuracy is highest. You can feel the echoes of Shannon's theory of communication. A channel with noise has a capacity measured in bits per second. To transmit reliably at higher rates, you spend more on signal power, on coding complexity, on error correction. Neural codes do compression and prediction because information about the world has structure. The statistics of natural scenes and sounds are redundant. You can represent them with fewer effective degrees of freedom if you choose good basis functions. Early visual cortex cells behave like filters tuned to edges and bars, exactly the sort of representation that captures the essential bits efficiently. In probabilistic terms, neurons attempt to carry surprise, the part of sensory input you couldn't have guessed. Predictive coding theories make this explicit population signal the difference between expected and received inputs, and these error signals flow to update internal models. Such a strategy saves energy, because you don't need to propagate what you already know. You send only the news. We learn in part by paying up front to build a good predictor, and we save daily by not retransmitting the obvious. Memory changes the wiring. Long-term potentiation and depression, the strengthening and weakening of synapses require new proteins, reshaped spines, and sometimes the growth of entirely new synaptic contacts. Those material changes are paid for in ATP and raw materials. Sleep contributes by scheduling maintenance. Lymphatic flow clears metabolites. Neuronal firing patterns replay and consolidate. Synaptic weights are pruned or normalized, so the network stays sensitive without saturating. None of this is a romantic flourish. It's energy arithmetic. Lessons are not stored in a metaphysical vault. They live in molecules and morphology that must be carried and serviced. What sets hard limits on brains as computers? Several things. First, heat. Each spike and each pump release heat. Too much local activity raises temperature and risks damage. Cooling is therefore a design constraint influencing brain size and vascular architecture. Second, space. Axons and dendrites take up room, and longer wires cost more to signal along. That's one reason many brains favor short-range layered circuits with a sprinkling of long-range highways. Third, time. The physics of membranes and channels sets characteristic timescales for integration and firing. There's only so fast you can open and close protein gates without error. Fourth, chemistry. The metabolites you can carry and replenish, the oxygen delivered by blood, the capacity of mitochondria. These set the sustainable throughput. The overall picture is not of a maximal machine straining every bound, but of a beautifully balanced machine, negotiating multiple limits, good enough in many dimensions rather than perfect in any one. Pull the camera back again. Organisms are information processing engines embedded in ecosystems that are themselves information-bearing structures. A forest remembers not in the literal sense of neurons firing, but in the pattern structure of roots and canopies and soils layered with organic matter in microbial communities tuned by history. That structure channels water, light, and nutrients in ways that make tomorrow's forest more likely to resemble today's. Disturbance writes new information clear a patch and pioneers arrive. Over time, succession reshapes the community. Even climate carries slow memory, ice sheets, ocean heat content, carbon in soils and rocks. These are integrators of past flows that condition future responses. And at each scale, free energy is spent to maintain the salient patterns. The rest is shed as heat. We can say something precise about maximum usefulness of energy in these contexts with the notion of exergy, the amount of work a flow can do before it equilibrates with its surroundings. Sunlight has high exergy relative to a warm radiating earth. A river at altitude has exergy relative to the sea. A concentration of glucose has exergy relative to the cytosol. Good design in biology or technology tries to cascade exergy. Through many stages, the high-quality input does the most delicate jobs first, like assembling molecules or making precise measurements. Its leftovers do cruder jobs like heating, and the last dregs are allowed to drift away. Leaves do this with photons, cells do it with electrons and protons. Cities try and often fail to do it with fuels and food. So the physics of information pushes us toward layered use, toward reuse, toward careful handoffs. The speed accuracy frontier also haunts evolution. Consider microbial chemotaxis, the act of swimming up a nutrient gradient. The environment is noisy. Molecules arrive stochastically at receptors. To decide which way to turn a bacterium must average signals over some time, but linger too long, and the world changes beneath it. There's an optimal window that balances information gain against delay, and the biochemistry of the flagellar motor sits close to that window. In immune systems, the recognition of foreign molecules plays a similar game. Scan too coarsely and you miss threats. Scan too finely and you attack yourself. The energetic costs of scanning, proliferating, and remembering shape where those systems settle. Even at the edge of sensation, we find the bills itemized. Rod cells in the human retina can respond to single photons. To do so reliably, they keep their dark noise low. Thermal activation of the photopigment must be rare, and they invest in amplification cascades that boost real signals above the floor. Those cascades are biochemical, and restoring them after each flash costs ATP. Hearing does something analogous with mechanical amplification by hair cells. Again, exquisite sensitivity is purchased with constant quiet work to maintain finely poised structures. At this point we might ask, is there any sense in which mind our stories, mathematics, music escapes the ledger? I don't think so, and I don't find that diminishing. Culture is a new kind of coupler, an arrangement of symbols that recruits many brains to reorganize matter faster and with more foresight than genes could manage alone. Writing stores patterns externally on clay or paper or silicon, lowering the energetic cost to keep long-lived memories. Institutions coordinate large-scale flows, food, fuel data at exergy efficiencies that can be improved by design. And science itself is a meta-coupler, a codified method for extracting reliable information from noisy observations, deliberately spending time and energy on controls and replication to save generations from fooling themselves. The ledger extends, the rules hold, the possibilities expand. There's a lovely symmetry in where we've arrived. At the bottom are quantum-level constraints, barriers, tunneling, fleeting, coherence, setting the fine texture for catalysis and light harvesting. In the middle are thermodynamic constraints, Carnot-like limits, Landauer's bound exergy budgets, shaping how differences can be turned into work and memory. At the top are algorithmic constraints, Shannon capacities, rate, distortion, trade-offs, governing how well information can be compressed, transmitted, and used under noise. Life weaves across all three. It chooses pigments and protein geometries that flirt with quantum advantages without demanding miracles. It builds membranes and pumps that sit near thermodynamic sweet spots. It develops neural codes and cultural practices that juggle accuracy and cost. The artistry is in the fit across layers. So when you think of energy now, don't picture just heat or light. Picture specificity brought from the flow, a base correctly paired, an enzyme waiting with an active site shaped to a transition state, a synapse tuned to fire at just the right coincidence, a memory consolidated in sleeping cortex, a note on a page that spares someone the work of rediscovery. Each is a local reduction of uncertainty paid for by global dissipation. Each exists because the sun shines, the earth cools chemistry, offers stable footholds, and evolution has had time to explore the space of couplers. And let me stammer the core once to lodge it. Information is physical, information is physical, information is physical. It lives in differences and differences cost. We can spend wisely or we can spend foolishly, but we cannot spend nothing. The good news is that the universe is generous with flows, and within the great constraints there is room for elegance. Where next? We've looked at the coins and the cash registers. Let's step into engines that push the frontier of coupling both natural and human-made. From the rotary marvel of ATP synthase to artificial photosynthesis, from the sodium-ion batteries inside bacteria to the electric grids we're learning to decarbonize, the same principles reappear. Next, we'll wander through these engines and ask how close to the bounds can we come, and what does good design mean when the metric is both truthfully scientific and beautifully humane. So we turn from counting to building. Let's walk into the workshop, nature's workshop first, then ours, and actually look at the engines. Engines are the places where gradients meet geometry, where differences are coaxed through channels, so that part of the fall becomes form and function before the rest drifts away as heat. We've mentioned ATP synthase in passing, but it deserves a front row seat. Imagine a turbine so small that millions could sit on the head of a pin, yet so precise that each rotation pays for 3 crisp clicks of the chemical coin ATP. Protons gathered on one side of a membrane find doors in a ring of subunits. As each proton takes a seat and then exits, the ring turns. A central shaft, the gamma subunit, twists inside 3 catalytic pockets, forcing them through a cycle-bind ADP and phosphate squeeze to make ATP release the product. It's a rotary engine that rectifies random motion. The proton gradient creates a bias, and the molecular architecture translates bias into steps. The elegance here is not only that it works, but that it works near microscopic limits of efficiency for its scale and temperature. It wastes some energy, everything does, but astonishingly little considering the thermal agitation all around. Upstream of that turbine sits an even grander engine room, the electron transport chain. In mitochondria, a procession of protein complexes and mobile carriers accepts energetic electrons from the breakdown products of sugars and fats. The electrons travel downhill in controlled drops, each drop coupled to the pumping of protons across the inner membrane. Oxygen waits at the end as the final electron acceptor, allowing the chain to reach a deeper valley than almost any other common chemistry can offer. It's a ladder down a cliff with the rungs spaced just right so the climber never slips or leaps. The safety rails are enzymes that prevent electrons from taking shortcuts that would spark reactive oxygen species. When the rails are stressed, cells can open shunts, uncoupling proteins that let protons meander back without making ATP, converting potential to heat instead of risk. In brown fat, this becomes a deliberate heater. You can feel the design principle: don't chase perfect efficiency at the price of catastrophe. Aim for robust optimums that hold under sloshing condition. Not every cell uses protons as the main currency across membranes. Some bacteria run on sodium gradients. The logic is the same: store free energy as a difference in ion concentrations, and it comes with advantages in specific environments. Sodium leaks differently, interacts differently with proteins, and allows motors and transporters tuned to that chemistry. Nature is a tinkerer. Once a coupler works, variations proliferate. You'll find sodium-driven flagellar motors, rotary devices that spin helical propellers to swim. The step size is quantized by the geometry of ion binding and release, and the torque depends on the flow. It's a direct kinetic metaphor turned reality, a river turning a wheel. Then there's photosynthesis, which is really a set of engines in series. First, a light harvesting complex, corrals photons. Pigments absorb light in particular bands and hand the excitation along a network, a relay that may, for fleeting instants, exploit quantum coherence to explore multiple handoff routes before settling on the best. The energy lands in a reaction center, where a carefully poised arrangement of molecules encourages an electron to jump to a higher energy acceptor while leaving its partner behind. That charge separation is the crucial trick. It creates an electrical potential difference from a photon's shove. The lost electron wants to fall back. The architecture instead channels it through carriers that pump protons and build the gradient. The gradient turns the ATP turbine. ATP and an electron carrier then pay for carbon dioxide to be fixed into sugars. Along the way, in oxygenic photosynthesis, water is split, protons and electrons captured, oxygen released. The oxygen evolving complex, a little cluster of manganese and calcium atoms, walks through oxidation states like clockwork, storing enough punch to pull electrons out of water. It is by any standard one of chemistry's masterpieces. Photosynthesis is selective. It doesn't try to swallow all sunlight. Pigments ignore some wavelengths, reflect others, hence the green of leaves, and shuffle their absorption with accessory pigments when the light regime changes. Too much light and the machinery risks photoinhibition, so plants and algae deploy non-photochemical quenching, safe ways to dump excess excitation as heat. The same principle appears again: ride the gradient but fit your coupler to the flow you expect, and open relief valves when the flow surges. If we were to sketch the design rules nature keeps rediscovering, they'd read like the backstage notes of a meticulous engineer. First, match the impedance. In radios and in cells, efficiency hinges on matching the source to the load, so energy transfers without big reflections or losses. Mitochondria adjust the redox state of carriers and the membrane potential, so electrons don't pile up at any one step. Leaves adjust stomatal openings and antenna sizes to the day's conditions. Second, minimize irreversibility where it matters. Every real process generates entropy. The art is to keep the big drops, the big losses only where you don't need fine control. Use small, near-reversible steps to assemble delicate structures, accept bigger off spills when you're just warming the bath. Third, exploit modularity. ATP as a universal coin, ion gradients as generic batteries, scaffolds like microtubules as rails. Once a good module exists, build adapters rather than reinventing the wheel. Fourth, build in feedback. Sensors for redox, state oxygen, light intensity, ion concentration. Closing the loop allows systems to stay near their optimum despite outside gusts and jolts. Fifth, accept graceful inefficiency for robustness. Perfect coupling is brittle. A small leak can stabilize a system against surges. A spare pathway can prevent overload. When we move to human-made engines, we're still playing the same music on different instruments. Heat engines from the piston in a car to turbines in power stations ride the difference between a hot source and a cold sink. The absolute ceiling for their efficiency is set by the Carnot limit, which depends only on those temperatures. Real machines fall short because real heat flows through finite gradients. Bearings, rub fluids, mix and combustion is messy. But the design instinct is Carnot's: raise the source temperature, lower the sink temperature, minimize sources of irreversibility like turbulence, where you want laminar flow, and extract work in staged expansions rather than a single violent bang. Modern gas turbines, especially when coupled with steam cycles to make combined cycle plants, leverage this staging beautifully. The hot exhaust from the first engine becomes the source for the next cascading exergy down the ladder, before releasing the final heat. Stirling engines gently compressing and expanding a working gas while shuttling heat in and out illustrate the opposite virtue: near reversible motion. They can, in principle, approach Carnot efficiency if run slowly with excellent heat exchangers. The price is power density, whisper, quiet thrift trades against speed. In between the Otto and diesel cycles of internal combustion, juggle pressure, volume and temperature, changes to harvest as much as practical from chemical potential, accepting losses in exhaust and friction as the cost of compact responsive power. Skip across to fuel cells, and you see biology's logic echoed: take chemical potential and step it down directly as electrical work, avoiding the detour through heat. A hydrogen fuel cell feeds hydrogen to one side, oxygen to the other. Catalysts split molecules and guide electrons through an external circuit, while protons move through an electrolyte. There's no slapdash flame, no churning piston, just controlled redox and ion flow. The limits here aren't Carnot, but the perfectibility of catalysts, the conductivity and stability of membranes, and the kinetics of oxygen reduction, a notoriously sluggish step. Even so, with good design, fuel cells can outperform heat engines at modest scales because they sit closer to the chemistry's native gradient. Photovoltaic solar cells also borrow a page from photosynthesis with their own twist. A photon arrives and excites an electron across a band gap in a semiconductor, leaving a hole behind. An internal electric field set up at a junction between differently doped regions separates the pair and directs them to an external circuit. The ultimate efficiency ceiling for a single junction cell under steady sunlight is bounded by a balance of losses. You can't capture photons with energy below the band gap. Photons far above the band gap lose their excess as heat, and some carriers recombine before being collected. Work through the arithmetic and you find a theoretical limit a bit, over a third of the incoming power under standard conditions. Real panels creep toward that ideal with anti-reflection coatings, textured surfaces to trap more light and materials with fewer recombination sites. Go multi-junction stack materials with different band gaps, and you can leap higher by slicing the spectrum into parts each harvested more cleanly. It's a technological echo of nature's accessory pigments. Both are spectrum management. Batteries are our portable couplers. A lithium-ion cell shuttles lithium ions between host structures during charge and discharge, while electrons travel through your circuit. The energy is stored in chemical potentials, intercalation energies, and redox states rather than in a bulk fuel. The design work sits in the material's science-stable electrodes that welcome and release ions without cracking, electrolytes that conduct swiftly but don't burn, interfaces that pass ions but block side reactions. Every charge and discharge nudges the materials. The entropy bill shows up as capacity fade and heat. Better chemistries, better separators, clever thermal management, all are ways to keep the cascade neat for longer. There's a bridge technology that delights the thermodynamic heart heat pumps. They don't convert heat to work, they move heat with work. Spend a little electricity to compress a refrigerant and you drag heat from cold outdoors to warm your room, or from your room to the outdoors to cool it. Because you're not creating heat, but relocating it, you can deliver multiple units of heat for each unit of electrical work. The limit is set by the same temperature contrast we keep circling. The closer the indoor and outdoor temperatures, the better the coefficient of performance. In a world seeking thrift, heat pumps are quiet champions. They respect the physics by coupling to forgiving gradients and letting the cold night sky be the sink it longs to be. At larger scales, the grid is a nervous system for energy. It balances supply and demand, second by second, blending many engines with many loads. Its deepest challenge is variability. Wind rises and falls, clouds drift, kettles switch on. The physics way to see the solution is to build cascades in time as well as in energy. Fast storage flywheels, supercapacitors, handles blinks and wobbles. Medium storage batteries, pumped hydro bridges, hours. Slow storage, chemical fuels made by electrolysis, heat in underground rocks or molten salt, spans days and seasons. Pair that with demand response, letting some load shift a little, in time without pain, and the system looks less like a frantic juggler and more like a choreographed dance. We're learning to treat variability not as a flaw but as a design parameter, just as leaves do with passing clouds. In laboratories and pilot plants, people are building artificial photosynthesis catalysts that split water into hydrogen and oxygen under sunlight, or that drive carbon dioxide toward energy-rich molecules. The hurdles are catalytic. Water splitting is hard, carbon dioxide reduction is harder, and keeping catalysts active for long lifetimes in dirty, real environments is harder still. Yet the prize is compelling. A fuel made from light and air, and water storable at scale, burnable with a clean conscience if paired to capture loops. Success here will look again like nature's pattern modularity, feedback tolerance for imperfection, and a ruthless honesty about losses. Speaking of honesty, let's bring in exergy because it's the compass that keeps engineers and ecologists pointed the same way. Total energy in a flow is less informative than the portion you can convert to work before it equilibrates with its surroundings. A kilowatt hour of electricity has high exergy. A kilowatt hour of warm water near room temperature has very little. Good systems spend high exergy where specificity is needed, precision machining, information processing, chemical synthesis, and use low exergy heat for bathing rooms or warming soils. Bad systems, by contrast, pour high exergy electricity into crude heating and let delicate tasks be starved. The goal is a ladder catch, the top rungs for fine work, step down, and let the last glow drift gently into the night. We can even pull aesthetic guidance from the physics. A well-designed engine, biological or human, sounds right. In cells that sound is conceptual, no screeching bottlenecks, no thunderous surges. In machines, it can be literal, a turbine's clean whir versus a misfiring piston's cough. Smoothness correlates with low irreversibility. We feel it in our bones when a device is fighting itself because excess heat vibration and noise are entropy escaping in all the wrong places. But every engine ages. Bearings wear catalysts, poison membranes, leak codes, drift. The physics doesn't bless immortality, it blesses maintainability. Nature excels here. Mitochondria divide and fuse, swapping parts and diluting damage. Chloroplasts turn over pigments, enzymes are replaced, DNA is proofread and repaired. Human systems are catching up with sensors, predictive maintenance, and self-healing materials. The principle is the same as always: spend a little continuously to avoid spending a lot catastrophically. So robustness is a budget, not a spell. Where does all this leave the story? We began energy as the capacity to move a system from the ordinary to the specific. via gradients and couplers. It leaves it with a toolbox and a charter. The toolbox includes turbines the size of viruses and towers that touch the clouds, catalysts that shuffle atoms, and networks that shuffle electrons. The charter is to honor the constraints, to treat the second law as a tutor rather than a tyrant, to place precision where it's rewarded to relax, where the ledger says relaxation is wiser than struggle. And there is one more engine to visit, perhaps the most human, the engine of design itself. Minds are heat engines that burn glucose to reduce uncertainty about possibilities. We make models, we run them forward, we adjust, spending ATP to save steel and coal and wind. The design loop is a thermodynamic loop. If we invest our cleverness up front, choosing tolerances, materials, controls, then the machine spends less exergy for the same function across its life. In other words, intelligence is a preheater. Pay a little in thought, save a lot in entropy. So let me stammer the credo we've earned: match the flow, match the flow, match the flow. Build the coupler to the gradient you actually have. Cascade the leftovers, feedback and buffer. Accept graceful loss when perfection would be brittle. Do this and your engine's leaf-lung turbine grid will feel as if they belong in the world, because they do. Next, I'd like to tilt the lens toward limits and frontiers. We've seen ceilings, Carnot, Shockley, Quasar for simple solar cells, Landauer for erasing bits, and we've seen how nature skates near some and artfully dodges others. Where are today's sharp edges? Can we compute closer to fundamental limits, sense more softly yet more precisely, or harvest diffuse flows like ambient heat or motion in ways that are genuinely useful rather than gimmicks? And how do we ensure that our pursuit of efficiency remains humane, that the patterns we preserve are not only intricate but worthy? We will take those questions carefully one by one and see what the ledger allows. Let's step up to the edge of the map, the places where our engines, our sensors and our computers lean against the fundamental bounds, and ask gently but firmly what the laws allow next. We've met Carnot for heat, Landauer for bits, and the rough arithmetic of exergy for systems. These aren't fences to bang our heads against. They're contour lines on the landscape showing where the slopes are steepest and where careful footwork is rewarded. The frontier, as I see it, is about learning to shape irreversibility to decide where we must spend entropy, where we can postpone it, and where we can turn an unavoidable spill into something useful on the way down. Start with computation, because modern life is computation rich. The textbook limit Landauer's small but stubborn cost to erase one bit tells us that if you truly forget, you must heat the world a little. Today's computers operate far above that lower bound. A logic gate in a contemporary processor dissipates many orders of magnitude more energy than KTLN2, not because the bound is wrong, but because we've chosen speed noise margins and manufacturability over hair's breadth thrift. Is there headroom? Yes. One path is reversible computing, if you arrange logic so that inputs can be reconstructed perfectly from outputs. No information truly destroyed, then in principle the Landauer toll can be deferred. Reversible gates like the Toffoli and Fredkin don't need to throw away bits, but in principle hides a world of engineering pain. Real devices leak, signals degrade, errors creep in, restoring crispness costs energy. The practical art is adiabatic switching, changing voltages slowly enough that capacitors exchange energy gently with inductors or reservoirs, rather than dumping it as heat. It trades time for reduced dissipation, slower edges, lower loss. Some experimental circuits have demonstrated dramatic cuts in energy per operation by embracing that slowness, but they won't replace your laptop's snappy processor tomorrow. The lesson is broader. When we can afford to be patient, we can often be kinder to the ledger. Another path is to change the medium. Superconducting logic uses Josephson junctions to switch quantum phases, with minute energy costs, with single flux quantum pulses as logic tokens. At cryogenic temperatures, dissipation can be extraordinarily low and clock speeds very high, making these devices candidates for specialized ultra-efficient accelerators or control planes for quantum machines. The price is obvious: refrigeration. Moving heat from millikelvin stages to room temperature is energetically expensive, and the whole system must be judged, as always, by end-to-end exergy bookkeeping rather than the seductively tiny losses inside the chip. Brains suggest a third path: computation that embraces noise and analog richness rather than fighting it gate by gate. Neuromorphic hardware, memristive arrays, spiking circuits, and mixed signal chips attempts to compute with probability distributions, time-coded spikes, and local plasticity rules. If you design the dynamics so that the system naturally relaxes towards solutions of your problem class, then each tick of the clock is also progressed down a free energy slope you intended. The reward is surprisingly high inference per joule. On tasks, brains excel at sensory classification control prediction in messy environments. The trade is universality and precision. Such machines are often brilliant at some things and mediocre at others. But that is again the physics whisper: match the coupler to the gradient you actually have. And then there's quantum computing, which tempts us with exponential leaps for particular problems by choreographing interference and entanglement. The thermodynamic ledger here is double-edged. On the one hand, a perfectly isolated quantum circuit performing unitary operations is by definition reversible. If you could keep errors at bay without expending effort, the computation itself would not generate heat by forgetting. On the other hand, reality insists on decoherence. Noise creeps in from control lines, materials, and stray photons, and we must push it back with error correction, redundant encodings, repeated measurements, and active feedback. Those acts of stabilization do throw away information about errors, and so they pay Landauer's toll. Whether the whole quantum stack can beat classical energy efficiency for problems of real interest remains an open, fascinating question, one that depends as much on materials science and cryogenics as it does on algorithms. The physics doesn't forbid thrift, it demands system-wide honesty. Turn now to sensing, where the aim is not to change the world, but to learn about it without ruining the very subtleties we seek. There's a general bound, often called the standard quantum limit, on how precisely we can estimate a parameter given a certain amount of signal and noise. We can improve our position by clever probe states, squeezed light that tames fluctuations in one quadrature at the cost of the other, by longer interrogation times, or by ensembles that average noise. This isn't esoterica, it is already on stage. Large-scale gravitational wave detectors inject squeezed vacuum to lower shot noise and tease out ripples in space-time smaller than a proton's diameter across kilometers of arms. Atomic clocks cool and trap atoms so that their quantum phases march in near-perfect lockstep, setting the tick of time by narrowing noise. In biology-flavored physics, single-photon cameras and low-noise amplifiers let us see under starlight conditions without bleaching the scene with floodlights. The trade never vanishes. Lower noise often means slower measurements, larger apparatus, or greater vulnerability to a different kind of disturbance. So good sensing is a choreography of compromises: quiet where you need quiet, loud where you can afford loud, and a place for each kind of irreversibility to land safely. The same spirit animates soft-touch sensing inside living systems. We already mentioned rod cells flirting with the single photon limit. Hair cells in the cochlea operate near thermal noise floors, using active processes to sharpen tuning. They spend energy to sit on the edge of a Hopf bifurcation, where small inputs yield large frequency, selective responses. In the lab, optogenetics and voltage-sensitive dyes let us watch neurons while trying not to perturb them too much. Force spectroscopy measures the tug of single molecules with springs as gentle as spider silk. Across all of these, the question is the same: how many joules must I part with to cut uncertainty by this much? And is there a way to pay in a currency my system handles gracefully? The harvest of diffuse flows is another frontier, a place where thermodynamics keeps us honest. Ambient heat at room temperature, random vibrations in a building, the faint flicker of radio noise, all are tempting sources for free energy, and all are treacherous if misunderstood. A classic result: you can't extract work from a single thermal bath at uniform temperature without another bath at a different temperature or a supply of low entropy structure. A little gadget that claims to power itself from ambient heat with no gradient at all is selling a Maxwell's demon without paying the memory bill. But there are gradients hiding in plain sight. The day-night swing forms one. The contrast between a warm surface and the cold radiative sky forms another, letting radiative cooling panels dump heat into the heavens at night, and with spectral trickery even under the sun. Thermoelectric materials convert temperature differences into voltage. Their efficiency is modest, but rising as we learn to scatter phonons, heat carriers, while letting electrons flow. Blue energy harvesting, the mixing of fresh and salt water at river mouths, converts a chemical potential difference into electricity via ion-selective membranes or electrodes. Triboelectric and piezoelectric harvesters nibble at mechanical noise to power sensors. They won't run a city, but they can untether thousands of tiny monitors and make the Internet of Things less hungry. Low-grade heat is everywhere: industrial processes, data centers, even the human body. The trick is to cascade it into tasks that suit its meager exergy: preheating water, warming greenhouses, feeding organic Rankine cycles that can eke modest amounts of work from small temperature lifts or driving absorption chillers for cooling. In cities, district energy networks turn this logic into infrastructure, piping heat and cold like water. In cold climates, heat recovered from servers can warm nearby homes. In hot ones, waste heat can be sunk to the night sky with radiative panels and good design. The physics is plain: don't pour high-quality electricity into dumb heating if you can move heat with a heat pump instead. Don't let low-grade heat escape without asking if a neighbour could use it. The ledger becomes most compelling when we ask it to evaluate whole systems, data centres, neighbourhoods, even nations. A data centre's primary job is to convert electric exergy into low-entropy insight patterns in data that help us act more effectively. But in the process, nearly all the input electricity becomes heat. Good design raises the temperature of the cooling loop so that the waste heat is not quite so wasteful, warm enough to feed district heating or industrial processes, while optimizing code and hardware to deliver more inferences per joule. At the algorithmic level, compressive techniques, sparsity, and clever caching reduce memory traffic, the true giant of energy cost in many modern workloads. At the device level, memory technologies that retain state without power, non-volatile elements, shrink the energy spent on writing and rewriting bits. And at the architectural level, moving the computation closer to where data is born, edge computing avoids flinging trillions of joules across continents, only to throw most of the inference away as latency. The same cascade logic appears writ in silicon. This is where humane efficiency enters. Physics can't tell us what to value, but it can sharpen our decision-making. If a city pours high-exergy electricity into resistive heaters, while letting food waste rot to methane in open dumps, the ledger points toward better couplers, heat pumps for space conditioning, anaerobic digestion, with capture for fuels, biogenic carbon turned into stable soil amendments. If a transport network idles combustion engines in traffic, the ledger suggests electrified mass transit and well-timed signals. If agriculture wastes water by pushing it against large pressure gradients at the wrong time of day, the ledger suggests drip irrigation and solar-timed pumping. In each case, the measure of better is not ideology. It's how many specific valuable patterns we can support per unit of exergy spent with the smallest collateral entropy in the wrong places. We should be candid about trade-offs. Pushing devices toward physical limits often narrows tolerance. A solar cell that reaches astonishing efficiency under concentrated light may demand exquisite tracking and cooling. A neuromorphic array that sips power may falter outside the statistics it was tuned for. A quantum sensor that touches the Heisenberg limit may require isolation that removes it from messy realities. The humane stance is not to pursue every last fraction of a percent of efficiency at the cost of resilience, but to choose a sweet spot where the system keeps its balance when the world wobbles. So robust optimums, again, not brittle utopias. Future frontiers glimmer. Room temperature superconductors, if ever realized with stability and manufacturability, would redraw exergy maps by slashing transmission losses and enabling magnet-heavy machines with few penalties. Solid-state batteries promise higher energy density and better safety, shifting what's feasible for vehicles and storage. Their practical hurdles, dendrites, interface stability, are deeply thermodynamic. Catalysts that split water or reduce carbon dioxide cheaply, durably, and selectively would make sunlight into storable fuels with fewer steps. The periodic table is generous, but it asks careful questions about orbital symmetries and surface energies. On the sensing side, atom interferometers and chip-scale optical clocks will leak into everyday tools, timing networks with absurd precision and sniffing gravity's gradients for underground water or voids inside structures. At the system level, grids that treat variability as choreography rather than chaos-layered storage, responsive loads, continent-spanning interconnects will feel as natural as a forest breathing with the day. All of these are at their heart instances of the same story. Find a gradient, build a coupler, place feedback to ride near the optimum, cascade the leftovers to someone who can use them, maintain the machine so small losses don't grow teeth, and wrap the whole in a culture that asks not only can we, but is this the pattern we want to sustain? A city can be an engine for human flourishing, education, art, health, or a sink that turns high exergy into traffic jams and heat. Islands. The laws permit both. They cheer for neither. They simply tally. Let me stammer the core tune once more to set the memory match the flow, match the flow, match the flow. When we compute, choose representations and hardware that meet the noise where it lives. When we sense, place our quiet where nature is loud, and our loud where nature is quiet. When we harvest energy, ride renewable contrast that the planet replenishes and cascade the rest. When we design, spend thought up front so that matter and energy spend less forever after. Where does this river run next upstream? Always there is time's arrow, the quiet fact that the universe expands, cools, and makes differences for us to ride. Downstream there is emergence, the way that coupling flows across many scales lets novelty appear without magic. I'd like to bring those together. How does the arrow of time, written in the statistics of trillions of particles, give rise to arrows of meaning, or goals, plans, purposes, in the minds of organisms like us? How do patterns that persist for minutes, ionic gradients, share the stage? With patterns that persist for centuries, languages, laws, landscapes, the physics won't give us morals, but it will give us a stage and a tempo, and it will insist kindly but firmly that every purpose must be paid for. So let's talk about purpose next, not as a ghost above the ledger, but as a special kind of flow shaped by memory, prediction, and choice, all honest to the Book of Energy. Let's bring it home slowly, carefully, with the same honesty we've tried to keep throughout, by holding in view the two things that have guided us from the start, that energy is conserved and that entropy increases. Those statements are not cold verdicts, they are permissive rules. They say there will always be a ledger, and there will always be a direction of flow. Within that flow, patterns can appear and persist for a while if they ride the gradients with finesse. Life is one of those patterns, minds are one of those patterns, and meaning our plans, purposes, and promises is a special choreography we layer atop the physics without ever stepping outside it. If you strip away the romance and ask, what's the simplest, faithful picture? It looks like this. The universe provides differences, hot and cold, concentrated and dilute, high and low, excited and relaxed. Engines, whether built by evolution or by engineering couple, those differences to do work, they move mass, separate charge, assemble molecules, correct errors, and store memories. Nothing is free. Every local win is paid for by global dissipation. Every bit remembered is a small pulse of heat sent outward. Every reduction in uncertainty is a modest increase in disorder elsewhere. But that doesn't make the local wins meaningless, quite the opposite. Because the rules are steady, the wins can be stacked. Over seconds and years and geological ages, they become forests, coral reefs, languages, laboratories, and laws. We have walked that terrain together, from proton gradients and ATP turbines to leaves that drink starlight, from enzymes sculpting energy landscapes to neurons that spend carefully to carry surprise, from ecosystems that cascade exergy through 100 niches to cities that can really choose whether to waste high-quality electricity on crude heating or to move heat with pumps and let fine work be done, where its precision pays. We have sketched the limits, a little catechism of bounds, Carnot for heat engines, Landau for bits, Shockley-Queisser for simple solar cells, standard quantum limits for measurements. We've seen how nature doesn't break those bounds but dances near them, and how good design in our hands looks suspiciously like good design in a chloroplast match. The flow buffer, the surges feed back the state, except graceful losses rather than brittle perfection. Purpose then isn't a ghostly extra. It is the name we give to shaping the flow with memory and prediction. A bacterium swims up a gradient because past experience has been written into its chemotaxis circuits. A seed germinates on a schedule because circadian machinery has learned the sky's rhythm. A person decides to build a bridge or write a proof because models in a brain anticipate consequences and assess costs. In every case, free energy is spent to make the model to keep it and to act on it. The dignity of purpose sits in that price. It isn't a dream floating above physics, it's a commitment stamped in ATP hydrolysis, in glymphatic cleanup during sleep, in synaptic proteins, ferried down axons by tiny kinesin walkers that take 8 nanometer steps and never once send an invoice. We pay as we mean it. If there's a single habit of mind that this journey suggests, it's to see cascades everywhere and to ask whether they are graceful. A graceful cascade catches high-quality input, early for delicate jobs, copying a genome, with fidelity machining a bearing, to tight tolerance, calculating a trajectory with just enough bits, and passes the leftovers through stages where less specificity is needed until what remains is warmth dispersing into night. A clumsy cascade squanders the top rungs on blunt tasks, forces precision without payoff, and leaves very little structure behind. The difference is more than engineering taste. It is a moral style grounded in physics. A school that spends exergy to light curious minds is a graceful cascade. A city that spends exergy to idle in traffic is not. The second law doesn't care which we choose. It tallies both in the same indifferent units. But we can care, and the laws will let us care effectively if we respect them. There's solace in the timescales too. The arrow of time supplies rhythms that can be tuned together. Fast flows, neural spikes, gusts of wind, ripples on a pond make chance and improvisation possible. Slow flows, ocean currents, soil formation, cultural traditions make endurance possible. The best patterns nest the fast within the slow, quick inference riding on metabolic steadiness, responsive grids riding on seasonal storage, youthful creativity riding on institutions that remember. When things go wrong, they often go wrong by uncoupling the tempos, fast decisions that ignore slow ledgers or slow structures that smother fast adaptation. Bringing them back into sympathy is part physics, part craft, part patience. So purpose becomes tempo matching as much as energy matching. It helps to hold a few images close. Think of a leaf. Photons nudge electrons. A tiny charge separation is born and preserved long enough to be useful. Protons gather, a rotary engine clicks, sugars are made, oxygen precious and reactive is released. The leaf is an accountant and a poet. It balances ledgers while sketching a shape that catches wind and light without tearing. Think of a mitochondrion, an inner sea held at a small voltage by protein pumps, a turbine spun by returning protons, the gentle warmth of a good inefficiency that keeps reactive sparks in check. Think of a neuron ions parted and rejoined across a membrane, like lovers at a train station. The cost of the reunion paid in ATP so that the next message can be clean. Think of a city pipes and wires and roads as the circulatory system, schools and clinics as membranes where high-quality energy is converted into knowledge and health, markets and courts as feedback loops that dampen runaway instabilities and amplify honest signals. And think finally of a night sky. Starlight is high exergy radiation crossing cold emptiness. Earth answers in long, redder wavelengths. Between those beams lies room for oceans, weather, growth and thought. We stand in that room. We are made of it. The energy that arrived here 8 minutes after leaving the sun is the same energy that lets you read and wonder and care. The entropy you export as heat tonight is the correct and lawful price of remembering something tomorrow. There is no bookkeeping trick to avoid it, and there is no need to avoid it. The art is to spend on the patterns you want to persist. Families, forests, knowledge, music, fairness, to keep them specific against the ordinary for as long as the gradients allow. People sometimes ask whether this physical framing strips mystery away. I don't think so. The mystery isn't in violating the rules. It is in discovering how much richness the rules permit. It is in realizing that a universe with a conserved energy and an increasing entropy can nevertheless produce ammonites and oak trees, Beethoven quartets and quiet acts of courage, satellites and sonnets and simple kindness. The physics insists that none of this is free, and that is what gives it weight. A kindness that costs nothing is a slogan. A kindness that costs glucose and time and attention is a steady flame in a drafty world. We can choose to keep such flames. So as we close, let me stammer the pulse we've kept, not as a flourish, but as a mnemonic you can carry. Match the flow, match the flow, match the flow. When you design a lab experiment or a livelihood, a power plant or a poem, look for the gradient, build the coupler, place the feedback and cascade the rest. Accept small losses that protect you from large ones. Spend free energy where specificity matters and save it where it doesn't. And remember that every bit of meaning you keep, every truth you preserve against noise has a physical shelter in the world, a place where heat is released gently so that order can last a little longer. All there is conserved. All there is enough to make a universe that thinks. All there is flows through you as you read and will flow on when you're done. If you listen closely, you can almost hear it, the soft turning of turbines in the dark, the steady fall of gradients, the quiet rise of form. That is the sound of a lawful cosmos making room for life and mind and purpose. That is the sound of a ledger that balances and yet leaves space, real generous space for care and craft. And in that space we get to choose for a while what patterns to hold. So let's hold the good ones.